So we left off last time talking about statically indeterminate beams, and we had the propped cantilever beam, which is pretty common, where you might have some sort of a load on it and then a prop here supporting it. That was a very common statically indeterminate situation. And then we also talked about a continuous beam, where the beam was continuous over multiple supports, like this, and putting a load on it, oftentimes a continuous load, like that. So I wanted to investigate this one a little more today and actually go through the numbers of that. And in preparation for doing that, I want to look at some general deflection equations. So let's look at, if you were to go back to Appendix C of your textbook or go through the derivation of these, for a simply supported beam of length L with a constant distributed load. And maybe we will go old school here and talk about the distributed load. We'll say it's Q. We could say this is a W, or maybe we'll say that's Q. That's the distributed load there. And we could say that the deflection at the center, which is going to incidentally be the maximum, would be equal to 5 times the value of the distributed load Q times L to the 4th divided by 384 E times I. And the other one that we're going to need is to look at, again, a simply supported beam. But this time we will look at a concentrated load at the center line. So we'll say that's L over 2, and this is L over 2. And maybe we'll go ahead and say that that load is P. And the deflection here at the center line, which is also the maximum incidentally, is going to be equal to the value of the load times the length cubed divided by 48 EI. So you could go ahead and derive those, or you could look in Appendix C of your textbook or other engineering handbooks and get those. Let's separate these off and say that these are in general. Okay, so the problem I would like to look at looks like this. Let's document it a little bit better. I'll say that I have a beam, and we'll put a support over here, and then a roller here, and a roller there, and we'll say that this is distance L, and this is distance L, so the length of the beam is 2L. And we'll put this distributed load over this thing. Continuous distributed. And we'll use our variable Q for that. So I'd like to come up with the reactions on that. I think that's going to be kind of interesting, and eventually I will then compare it to what happens if we were to just put two beams side by side, and I think there'll be quite a bit to be learned with that. Well, I'm going to go ahead, and if I were to put these in as forces, we could say that we had a reaction here, and we had a reaction here, and we had a reaction there. And of course we would have a reaction there, but we don't have any horizontal load, so that one would be equal to 0. We see then 3 reactions in the vertical direction. We recognize that as a statically indeterminate problem. So I'll take this middle one as the redundant. Using the middle one as the redundant, I'm going to release the structure, and I end up with something that looks like this. You could imagine if you were to come in and knock out this one as the redundant, you would have, it would definitely sag out of shape. And sometimes you see this all too vividly. They'll have a beam, there'll be a post in it, and someone will want to remove the post, and indeed it sags down. Luckily, it usually doesn't come crashing down, but sags down pretty significantly. So we'll have something like this, and there's our load. Again, Q, And the thing we have to keep in mind is that this span is 2L, so that's going to be important when I go up and look at these equations that were made for L. So I can talk about the deflection here. The deflection in this case is going to be equal to 5 times Q times, let's see, if I've got the length here is L and this is 2L, so I'm going to have 2 to the 4th L to the 4th divided by 384 EI. And then I can't just do that without dealing with this redundant. So let's say that I come back and I put this redundant in it. You could imagine if you were to take everything off and just put that redundant back, it's going to look like a camel's back, bow out this way. And again, we have to remember that this distance is 2L, that this is acting at the center line, and we could say that this is our reaction R that we're looking at there, that redundant one. And if I look at the deflection here, I can say that that going up and using this equation here is equal to R instead of P, and then this length here is L, and I have 2L, so I'm going to have 2 cubed L cubed divided by 48 EI. Okay, what we're going to do is we're going to set these equal to each other. They're going to be equal. So we could say then that 5Q 2 to the 4th L to the 4th divided by 384 EI is equal to R times 2 cubed L cubed divided by 48 EI. And in solving R, we can say that R is equal to, I'd multiply both sides by 48, then cancel the EI out. And that is probably worth talking about for a moment. Sometimes in beams, the stiffness may not be the same in both directions. You could imagine if this was a reinforced concrete beam where the cross-section of the beam looked like this and we had rebar there, the stiffness of that beam would be very different in both directions. So we're assuming that it's probably not like that, and rather it's a more homogeneous beam, a wood beam where it has the same species and type of wood top and bottom. We could go ahead and do something like that. But that's something to think about to make sure that E is the same so that we could cancel that out. Of course, I would be the same. We could cancel that out. And we come up then with R being equal to 5 times Q times 2L divided by 8. And we get finally that we have 10 over 8 times QL, or WL, depending on what variable that you want to use. So that's a good result there. That would be this force. We could put that in then. This redundant is 10/8 QL. Now, what I would like to do, so that's the redundant one there. What I'd like to do is find these other reactions and then look at what I was talking about. What if we had a beam that was just two sections of beam put together? So I'm going to hang on to this. Go to the next page and say that if we're looking at this beam, then we've got a reaction here. We've already agreed then that this one is 0, the horizontal. We've just found that this was 10 over 8 times QL, and we have a couple unknowns here. Maybe we'll call this R1 and R3. That presumably would have been R2 possibly. And we've got this distributed load of value Q or W. I'll take Q. We've got the length L. So if I go through summing the moments about the left-hand side, setting that equal to 0, what would I have? I would have this force here, which is going to be 10 over 8 times QL, acting through a distance of L, right? And then plus R3 acting through a distance of 2L. And then I would have to subtract off the load up here, which is going to be Q times 2L times the distance at the axis, which would be at the center point here. So that will be L. So when you solve this then for R3, R3 turns out to be equal to 3/8 QL. And you go through the math and all the smoke clears on the thing. 3/8 QL. So then if you sum the forces in the vertical direction, setting that equal to 0, you have R1 plus 10/8 QL plus 3/8 QL minus 2 QL is the total load down. So then R1 would likewise become 3/8 QL. Okay, so maybe we will put our findings over here and talk about if this beam is continuous. We end up with reactions that look like this. We have 3/8 QL. We have 10/8 QL. And we have another 3/8 QL to support this total load of 2 QL. And hopefully that works out. If we look at adding 3/8 and 3/8 and 10/8, that gives me what, 16/8 or 2 QL. So with that does work out. Okay. Well, I'd like to compare this with a situation where we just have two shorter beams and we put them together. And they're then fit like this. And you could imagine if this was Q and this was Q and this length was L and that length was L, this would have to support half of this one, so that would be what, QL over 2. And over here we'd have half of this one, which would be QL over 2. And then if I have QL over 2 from this one and QL over 2 from that one, the combination here, when I add those together, would be QL, wouldn't it? Okay, and we get really a different situation with the continuous beam here. The end reactions are less and the middle reaction is more. That's why sometimes when we're going in and doing a remodel or something, if we have a continuous beam, we can take advantage of that, or sometimes we don't want that. Maybe we don't have the footing size to support this, and we would like to reduce this a little bit, going from 10/8 down to just 1. And we'll talk about actually cutting through that. Usually you just prescribe cutting through that and then tie it together with some sort of a strap so it doesn't separate in an earthquake or something like that. But sometimes this is an advantage and sometimes this is an advantage. And the biggest thing that hopefully you take away from it today is that they are different. That a continuous beam is a statically indeterminate situation, and it's going to net different support reactions. And then if you were to take this one step further, it would have a different shear and moment diagram. They would have different shear and moment. So the structural folks will go on and talk about that more next year. But I wanted to use this as a good example of a statically indeterminate problem that nets some kind of unintuitive results. A lot of people might be lulled into thinking that the reactions would be the same in both cases, and they actually are not. So I'll leave that, and let me double check my work here, make sure that that is correct. I think we're good with that. Well, the last thing that I want to do with beam deflections, we talk about statically indeterminate, is I'd like to apply this in maybe a more real-life situation. So I'd like to go back to the garage that we were talking about building, the man cave, so to speak. And I'm going to change the dimensions on this just a little bit so it'll work better with some of the materials that I want to use. But let's say that I want to build a garage. Looks like this. We'll put a door in it here, and We'll say that this door is a 12-foot door, so we get a car in there and have it half in, half out with the doors open, maybe if we're doing some work on it or something. And we're going to say that this is a little shallower than I think we had in the past. We'll say 24 feet, so we can get one car in there and walk clear around it, no problem. And if I look at a section through this, what this section is going to look like, let's say that we arrange our roof, so we'll keep this very simple here so we don't have to worry about eaves and whatnot. But we'll say that we have something like this. Where I guess the front wall, that's through the beam, right? So I should probably put that beam on there. Okay, so we've got this beam here that has to sit on, and we've got then the slab here, like this. Okay, that's kind of what we would have. And our load down on this would be something like this. We'll just figure standard roof and ceiling, standard insulation, standard light fixtures and whatnot, and we'll look at this distributed load as about 15 pounds per square foot dead load. We'll take it around here where we have 25 pounds per square foot snow load. Now the structural folks are going to want to keep those separate, but for our purposes, because the snow load stays a lot shorter period of time than the dead load, but for our purposes, we'll just add those together and take 40 pounds per square foot. Okay. So if I look at this beam, if I look at this header that's going to be in here over this garage door, and look at what we have there, that's going to look something like this. We said the span was 12 feet. Okay, and we might have to go 12'3" depending on the bearing length and the dimensions of the door. But we'll just take the nominal distance as 12 feet there. And then what load are we going to have here? Well, it really needs to support what? Half of the roof. So if we go down through it, this portion of the roof here is going to go into the back wall, whereas this portion of the roof here is going to go into the header. So if I have 24 feet, this would be, I've got to support this 12 feet there. So if I take 12 feet of roof times 40 pounds per square foot, I end up with what, 480 pounds per foot. Okay, I think that's what we've got because we're supporting 12 feet of roof here. And I got an awful lot of 12s. We've got a 12-foot span. We're supporting 12 feet of roof, but I think we'll be okay. Now I think what I will do, excuse me, is maybe say that maybe take this to about 500 so that I can include the dead weight of the beam, dead load of the beam. So I'm just going to go ahead and analyze this at 500 pounds per foot. Okay, so if we have a 15 to 25 pound beam, we're probably still okay. So I take the what we calculated at 480, I add a little bit extra to it. So I don't have to go back and worry about the dead load of the beam once I size the beam, and we should be good to go. So with that, I know from a distributed case that my maximum moment is equal to WL squared divided by 8, or QL squared divided by 8, whichever variable you like. So when we go through this, we could say that we have 500 times the length, which is going to be 12, that's the span of this thing, up there, squared divided by 8, which we end up with what? $9,000, and that's going to be pound feet. And then if I multiply that by 12, I end up with 108,000 pound inches, which should work better for my calculations. Now I'm going to try and use saw lumber. So let's say that my maximum bending stress sigma is going to be 1,000 psi for Doug fir number 2 that we have around here. That's pretty close to what it would be. My shear stress tau would be about 100, probably 95, but we'll call it 100 again for Doug fir. And E we'll take as about 1.7 times 10 to the 6th psi. So those are the numbers that I have to work with. So what I'm going to do is I'm going to come over here and use that sigma is equal to minus my over I, and I can change that a little bit and say that's also equal to m over s, the section modulus. So, and that would be a symmetrical beam, and I'd have to keep track of the tension or compression. That's why I don't have the negative sign there. So if I rearrange that a little bit, I can say that my section modulus is equal to m divided by sigma. So if I put the moment in there, 108,000 pound-inches divided by 1,000 pounds per square inch, psi, gives me what? The pounds cancel, and I have 108 inches cubed. And we could, if we wanted to, set this equal to, remember this, for a rectangular section, like we're probably going to have, this would be base times height squared divided by 6. We could put that in there if we wanted to. But I think I'll just go to the table like we've had in the past. So I go to this saw lumber table. We'll put this as page number 4. And we want to be in this column here. And probably we're not going to get any 2-bys to work, 3-bys, 4-bys. We get 102. We'd have to do a 4x16, which isn't that common, although it would be kind of nice. We could get it in a 2x4 wall at the front, although we start to lose some headroom with 4x16. If we want to do that, we'd probably go with a glue lamp. But I'm going to look at 6x. We just do a 2x6 wall in the front. We can do 2x4 walls on the rest of it if we wanted to. So right there should do it, shouldn't it? So it looks like a 6x12. Okay. So if I could say use 6x12. And let me look at a few things about this. What is the area on this? The area turns out to be 63.25. So the area, that's the cross-sectional area here of that thing. The area is 63.25 inches squared. And so I'm using this number here. And another number that I'm going to want is the weight per foot. So the weight would be 15.4 pounds per foot. So how did I do? Well, I had come up with this calculated at 480, so I added the other 20 to get 500. So I think I'm okay. I've accounted for this. So from a bending standpoint, we're okay at a 6x12. Now, there's other things we have to check. We've talked about shear, haven't we? And we know that tau maximum for a rectangular section would be 3/2 V over A. I think some people struggled with that on the midterm exam, so hopefully they know that better than ever now. Nothing like losing a few points on a exam to really emphasize things. So let's look at this. What's our reaction going to be? Well, if I use this 500, I'll say that this would be 500 times 12 divided by 2, right? So what do we come up with? 3,000? So we've got 3,000 pounds. So that's V, and then I've got the A, that's the cross-section there, comes from the actual dimensions of the beam. So we'll do 3/2 times the shear, which is 3,000 pounds. And actually in wood design, we could only have to look at the shear to the depth of the beam, so I get to discount a little bit of that. But for our purpose, we'll just take the 3,000 and then divide that, and that would be pounds. And the area, 63.25 inches squared. So we come up with 3,063.25, divide that, 71.1 psi, which is less than the 100 up here. So we designed it based on this 1,000 and came up with a 66 by 12. We checked our 100. That's less than the 100. So we're okay with that. Now the last thing we probably need to do is check with the deflection. No one wants a garage door that looks like this. So no one wants to see their structure like this, and we have a garage door that has bowed down like that. No one wants that, because then you end up with a roof line that looks like what? Like that. And a lot of times you can actually see whether a structure has started to fail or not by just looking at the roof line. A lot of times consulting, I could tell whether there's a problem or not as I drove up to the structure. But anyway, we don't want this. So what we're going to do is we're going to have to check the deflection. So we've done this in the past. We've done the bending. We've done the shear. But we're going to take the added step now of looking at the deflection. And if I go to my equations in Appendix C, we've already used those once today, but let me put them up here. So this is page 6. We just have a simply supported beam with constant distributed load, so our maximum deflection is going to be right there. We've used that minus WL to the 4th over 384 EI. We didn't have that negative sign because I take positive down, so let me put that up here with this beam. We said we had 3,000 there and 3,000 there, 12-foot span, and we calculated 480, but we added the weight of the beam in there, so we said this was 500 pounds per foot. So we can say that the maximum deflection, which incidentally in this case would be at the center line, it's not always at the center line, but that's going to be 5 times W, or I think in the previous example I used Q, I'll use W here, 5 times W times L to the 4th divided by 384 EI, right? Okay, so maybe we want to run back here and write down what we know about this. We've got that E is 1.7 times 10 to the 6th. PSI. That'd be for Doug for number 2. Then I got the area and I got W, but I didn't get I, did I? So I better say if this is E, then we have I. And go to this table and get I. What's I for this thing? The 1-1 axis, 697.07. Let's just call that 697 inches to the 4th. And of course that comes from base times height cubed divided by 12, that equation right up there. Okay, so how are we doing here? We've got our equation, we've got E, we've got I, we have W, we've got the length. So I think we can do that. And as you go through these, until you get really familiar with this, I encourage you to really watch the units on this. So let me be very careful with this. 5 times W, which is 500 pounds per foot, times the length, which is 12 to the 4th, then I'll get feet to the 4th, divided by 384, and then I have E, which is 1.7 times 10 to the 6th pounds per inch squared, and then I have I, which is 697 inches to the 4th. So as I go through this, I get to cancel that pound and that pound. And then I get to cancel inches squared there with a couple of those. And then I get to cancel one of these with one of those. So I'm left with that. So I've got feet cubed over inches squared. And mind you, these are fairly common units. We've got the length in feet, E and I are all in common units, W's in common units. So this is a real nightmare waiting for you in terms of a units mistake. Because we're going to have to multiply by 12 cubed inches cubed and a foot cubed, right? 12 cubed, inches cubed, and a foot cubed. So I get to now cancel this with that, and then I've got that I can cancel with all but one of those, and I'm left then with inches, which seems like a reasonable unit for deflection. And had I not been careful with the units, I would have been off by this 12 cubed, 1728 or something like that. So we would have been way small on our deflection, and thinking if things were okay, and maybe it was deflected way out of shape. So let me go ahead and run the numbers on this then. So I come up with 0.197 inches, which seems fairly reasonable. I think I'll take the time and double check my number here. This is maybe not the greatest example because this 12 cubed, this is from units, whereas this 12 to the fourth, that is from the length to the fourth term. But other than that, I think we're okay. Let me double check this. Yeah, I got that answer twice. I think we'll be okay, hopefully, with that. So, looks like, what, 2/10 of an inch? That starts to seem reasonable. We're probably not going to see that. We might be able to see that sag, but remember, that's with full snow load, so snow will melt. Hopefully, it'll come back a little bit. I worked with a great contractor one time, and he always didn't want to have a lot of deflections. He liked to build a really good house, prided himself on that, and he always said, well, I only want 1/10 of an inch of deflection. And in a small span, you can probably get that, but a large span, you really can't get that. And we don't necessarily talk about the maximum deflection in terms of a number. What we do is we talk about it as a ratio of the length. So if we're just building a shed or something, maybe we talk about L over 240. Or maybe we talk about L over 360. If you're looking at roof beams, L over 240. If you're looking at floor beams, the lowest you can go is L over 360, and that's pretty tacky. You'd really, if you're going to build anything decent, you want to look at floor beams L over 480 at least. When you start looking at maybe putting masonry on top of it, you don't want to have things cracking on you and whatnot. You might be getting up into the L over 700 range and on up from there. Obviously, you're going to have more deflection down here. And up here, it's going to cost you more. So that's usually the way it works. As you get less and less deflection, you have to put bigger and bigger beams in it, and it costs you more. Well, let's go ahead and on this one see what we've got. What if we wanted to analyze L over 480? So if I take L, the length over 480, the length on this thing, and I'm going to do the length in inches. If I have 12 feet, I would have 144. So that's 12 feet, which is 144 inches, divided by 480. So what's that turn out to be? 0.3. So our deflection here is smaller than L over 480. So I think we're okay on this too. So I think at the end we've got a good selection. We've got this 6x8 that we chose based on bending. We checked it for shear and it was good, and then we checked it on deflection. So I think our final call would be that 6x12 And we'd obviously want to say what grade it is, probably dug for number 2. We'd want to say what the maximum span is so no one mix that up. The other thing we probably need to talk about is what kind of columns or trimmers that we would put underneath this thing, and then down to the foundation. So if we look at what's going on with that beam, we'd have some supports here, and then we'd have a foundation there. So we'd probably have to talk about bearing there also. So a lot of other things before we got final design. But I wanted to go through this before we finished up with beam design and look at this and incorporate this deflection equation into our beam design to make sure that we don't have uncontrolled deflection and the deflection getting out of control. Well, that finishes up our work on beam deflection. You've got quite a few homework problems and can be fairly involved in this area. And where we will go next is looking at columns, which we've got a nice example of this right here. What do I have to do to keep that column from buckling? And we're going to have to look at some differential equations to do that. So that'll be kind of fun. Be the last section that we address as we finish this up. I don't think that this is page 5. I think I got my page numbering off. Maybe not. So, well, I will sort that out and post the PDF. I'll take care. I'll see you next time.